The James Webb Space Telescope has just unveiled the most detailed look yet at 3I/Atlas, the third known interstellar object. New data suggests it may be far larger than anyone expected, challenging long-held beliefs about how other star systems eject material and what's really drifting between stars. This marks the arrival of a star system wanderer. On the 1st of July, 2025, the Atlas Survey Telescope in Chile spotted something unusual, a faint object streaking across the sky. At first, it looked like a standard comet, but within hours, its trajectory, velocity, and angle told a very different story. This wasn't a solar system object. Its path was hyperbolic, its speed too fast to be gravitationally bound to the sun. Scientists confirmed it. This was 3I/Atlas C/2025 N1, the third known interstellar object to pass through our solar system. Unlike the previous two, 1I/Oumuamua in 2017 and 2I/Borisov in 2019, this one was detected early. We had months to study it before it reached the sun. That lead time turned a curiosity into a scientific opportunity. The fact that it's interstellar is no small detail. It means everything about it, its composition, behavior, even its size, might not follow the patterns we expect from solar system comets. Its 3D motion cuts across the ecliptic plane, suggesting a random origin. And that randomness matters. It gives us clues to the structure of other planetary systems light years away. This object was born under a different sky, said one astronomer. Studying it is like receiving a postcard from another star. And so the mystery of 3I/Atlas doesn't begin with how large it is, but with how it arrived fast and unbound, rewriting the rules as it crossed our sky. Why does size matter? It comes down to nucleus versus coma. When people hear, how big is it, they imagine a solid ball of ice and rock. But with comets, what you see isn't always what you get. The visible glow, the coma, isn't solid. It's a cloud of gas and dust expelled by the nucleus, the true core. But that core is often hidden, blurred by the brightness surrounding it. That's the challenge with 3I/Atlas. Early observations from the Hubble Space Telescope put an upper limit on the nucleus, no more than 5.6 kilometers across. But infrared measurements from ground telescopes hinted at a much larger object, maybe even up to 40 or 50 kilometers, depending on how efficiently the object reflects sunlight and re-emits heat. This matters deeply. A larger nucleus means more mass, more stored volatiles, and likely a more violent or ancient history. It could mean 3I/Atlas formed near the CO2 ice line of a distant system, or that it's been traveling through interstellar space for millions of years, shedding material as it goes. But if it's that big, why haven't we seen more like it? That question sparked debate. Some scientists argued that a large interstellar object would imply a larger population of similar bodies. Yet, we've only found 3 so far. Others think it's just a matter of detection limits. We're only now getting good enough to see these kinds of visitors. In the end, knowing its size means knowing its origin story. And to find that out, scientists needed more than Hubble. They turned to a telescope with a far better view, James Webb. The James Webb Telescope turned its eyes. On the 6th of August, 2025, the James Webb Space Telescope, JWST, locked onto a rare target, 3I/Atlas. With its powerful near-infrared spectrograph, an IR spec, Webb began collecting data that ground-based telescopes couldn't. It wasn't just looking. It was measuring, not just observing, but decoding the object's chemical fingerprint. Unlike visible light telescopes that struggle through dusty comas, Webb's infrared vision pierces through the fog. It can detect water, H2O, carbon dioxide, CO2, and other volatile molecules. These are key clues to where the object came from and what it's made of. This gives astronomers indirect insight into the nucleus size, since the rate of outgassing depends on the surface area of exposed ice. This isn't just about seeing something new, one mission scientist explained. It's about understanding what it's made of and what that says about where it came from. With Webb's data, researchers began assembling a clearer picture. They could estimate how much gas was being released, how fast dust was being expelled, and how that tied back to surface activity. This told them how much active area the nucleus must have, and by extension, how large it likely is. More importantly, Webb's involvement shifted the story. Before, 3I/Atlas was a rare guess. Now it became a benchmark, an object measured not just by light, but by chemistry. It went from mysterious to model-worthy, a case study in how to analyze interstellar visitors going forward. And what Webb revealed in that spectrum hinted at something strange, chemistry that didn't quite fit the solar system norm. Unusual chemistry provides clues to size and history. What Webb found wasn't just typical comet stuff. Its data showed a surprisingly high ratio of CO2 to H2O, much higher than we usually see in comets born in our solar system. This unusual chemical signature raised immediate questions. Normally, solar system comets release far more water vapor than carbon dioxide, but 3I/Atlas seemed to have flipped that ratio. This suggested one of two things. Either it formed much farther from its parent star near a region where CO2 ice is stable, or it's been wandering through interstellar space for eons, slowly losing more volatile ices over time. Either way, it painted a picture of something old, cold, and alien, possibly formed beyond the outer edges of a planetary system, or even flung from a system unlike ours entirely. The chemistry is a memory, said one astrochemist. It tells you where something's been, what it survived, and how long it's been on the road. The high CO2 also implied something else. A larger surface area was needed to drive the outgassing Webb detected. That in turn hinted at a larger nucleus, or a highly porous, active one with more exposed ices than expected. So with each spectral line, Webb wasn't just reading the comet's atmosphere. It was unwrapping its size, structure, and story, one molecule at a time. The true size debate ranges from kilometers to tens of kilometers. At the center of the 3I/Atlas mystery is one question that refuses a simple answer. How big is it really? For most comets, the visible brightness is dominated by the coma, a halo of gas and dust that expands as the comet heats up. But when an object is from another star system, and we've never seen one quite like it before, estimating its true nucleus size becomes far more complicated. Initial readings from the Hubble Space Telescope gave a conservative estimate, placing the nucleus at no more than 5.6 kilometers in diameter. That's based on how much sunlight it reflects and how its coma spreads out in visible wavelengths. But infrared observations, especially those measuring thermal emissions, suggested the nucleus might be much larger. Some estimates push the diameter as high as 46 kilometers, depending on assumptions about albedo, surface reflectivity, and thermal inertia. This wide gap triggered a heated debate. Harvard astronomer Avi Loeb and others suggested that if the infrared signals were accurate, this would make 3I/Atlas not only the largest interstellar object ever observed, but also evidence that large icy bodies could be common in the galaxy. That would have sweeping implications, requiring models of planet formation and ejection mechanisms to accommodate objects far more massive than previously expected. But not everyone agreed. Critics argued that such a massive nucleus would likely produce more visible dust, create a denser coma, and appear brighter at certain wavelengths than observed. If large interstellar comets like 3I/Atlas were common, why haven't we seen more of them already? One planetary scientist noted, if it's really 40 kilometers wide, we need to rethink everything we assume about how planetary systems shed debris. That's a lot of mass to throw away. The uncertainty remains, but Webb's data helped tighten the boundaries. By measuring the rate of volatile release, how much gas and dust is escaping the object per second, scientists can estimate the minimum surface area needed to sustain that level of activity. That in turn constrains the size. If too small, it wouldn't produce enough outgassing. If too large, its coma and brightness would look very different. Still, it's not settled. Different models still produce different size estimates, depending on which assumptions you make about the composition, surface texture, and how efficiently it reflects or absorbs sunlight. And unless a telescope can resolve the nucleus directly, an enormous challenge given the distance, the debate won't be closed. But one thing is clear. 3I/Atlas, whatever its true size, is forcing us to recalibrate. It may not just be bigger than Borisov or Oumuamua. It may be bigger than we ever thought interstellar objects could be. Activity and outgassing provide evidence of size and motion. If you can't see the nucleus directly, you look at what it's doing. And 3I/Atlas is doing a lot. Since its discovery, astronomers have tracked its coma, tail, and the steady outgassing of volatiles into space. These plumes, streams of gas, and fine dust aren't random. They reveal not only the chemical makeup of the object, but also the physical activity happening at the surface. Webb's observations revealed a mix of fine ice grains, larger dust particles, and distinct jets of CO2-rich material. These streams suggest active venting from localized spots, possibly from fissures or sunlit regions where ices are rapidly vaporizing. And that kind of outgassing ties directly to the size of the surface area available. A nucleus only a few kilometers across would struggle to support that much activity unless nearly every square meter was exposed and active. This behavior suggests either a larger than expected nucleus or one that is unusually porous, full of internal tunnels and voids where trapped gases can build pressure and escape explosively. You can't get this much gas from a simple snowball, said one mission scientist. It's got structure, deep layers, active zones, maybe even internal heat sinks. In the case of 3I/Atlas, what we observe in its motion helps map its unseen structure. The speed and direction of the jets affect the shape of the coma and even nudge the object slightly off its expected trajectory, a phenomenon known as non-gravitational acceleration. This effect, measured with incredible precision, tells scientists how gas jets push the nucleus, allowing them to estimate mass and surface dynamics indirectly. And here, the interstellar nature of the object matters again. Unlike solar system comets that have been sun-warmed on past orbits, interstellar comets may carry unprocessed ices, materials that have never seen intense sunlight before. As these pristine ices sublimate, they release energy and particles in different ways, often more violently and unpredictably. All of this outgassing, tracked by Webb and ground-based telescopes alike, creates a moving fingerprint, a pattern of motion, light, and chemistry that points back to how large the nucleus must be to support such dynamic behavior. 3I/Atlas is not just a frozen rock on autopilot. It's active, expressive, and through its outgassing, it's telling us how much surface, how much mass, and how much history it carries with it as it leaves our solar system behind. Why this size and object changes the game. If 3I/Atlas is truly 30 to 46 kilometers wide, it will be the largest interstellar object ever observed, and it changes everything. The two prior visitors, Oumuamua and Borisov, were much smaller, but 3I/Atlas may be 10 times larger with more mass, momentum, and the durability to survive extreme conditions in another star system before drifting into ours. This isn't just a visitor. It's a survivor of ancient chaos, said a planetary formation expert. Its size implies something bigger, that massive interstellar objects might be more common than we assumed. For decades, scientists believed such objects were rare, too small, or faint to detect. But if something this large slipped in unnoticed until recently, we may be missing many more. It challenges models of planetary formation. Maybe star systems eject not just fragments, but planet-sized bodies. And if they're out there, they may be delivering organics, seeding new systems, or threatening them. 3I/Atlas isn't just a comet. It's evidence of a richer, more active galaxy, one filled with silent travelers, ancient remnants, and stories waiting to be uncovered. And it pushes us to ask, how many more are out there passing by unnoticed in the dark? The limits of the data and what Webb added. Despite the James Webb Space Telescope's detailed observations, one thing remains elusive, a direct image of 3I/Atlas's nucleus. Webb revealed complex chemical signatures and precise outgassing rates, but the solid core is still hidden behind its bright coma. This isn't due to error, it's physics. The nucleus is tiny, the coma enormous, and no current telescope has the resolution to separate them cleanly, especially with the object moving so fast through space. Instead, astronomers rely on indirect methods, analyzing brightness, modeling gas versus dust emissions, and measuring infrared flux. It's not perfect, but it works well enough to define a size range. Webb helped most by identifying CO2, H2O, and carbon monoxide, key to calculating outgassing flux. That told scientists how much surface must be active, narrowing estimates of the nucleus's size. Webb didn't give us a photo, said a NASA scientist, but it gave us a chemical outline. Still, models depend on uncertain factors like albedo, grain size, and thermal properties. So, scientists speak in ranges, not absolutes. Yet the unknown is shrinking. Webb brought us closer, but the nucleus remains a silhouette, a target science can't fully touch. And that's what makes 3I/Atlas so compelling. It's still just beyond reach. What's next? Size, exit trajectory, and future visitors. On October 29, 2025, 3I/Atlas reached perihelion, its closest point to the Sun at just 0.36 astronomical units. Now, as it moves away, its coma fades, dust production slows, and a rare opportunity emerges, a clearer look at the nucleus. With less activity masking it, astronomers may soon detect the core more directly, helping to refine size estimates and study its surface. Telescopes like the VLT, ALMA, and Hubble are already lining up for follow-up observations before 3I/Atlas disappears into deep space. Looking forward, the Vera C. Rubin Observatory, set to go live in 2026,